waves. And waves, this comes right after our simple harmonic motion unit. Waves are periodic disturbances, vibrations, oscillations that transmit or transfer energy along a medium. And a medium is just the thing that the wave travels through. So right now my sound waves are traveling through the medium of air. If I shine a light, the light waves are traveling through the medium of air. Light from the sun is traveling through no medium. It turns out electromagnetic waves, light waves, don't require a medium. Sound waves do. So water waves, of course, the medium is water. So medium is just a fancy term for what it travels through. So generally it starts with, in this class, we're mostly going to start with, it could be any vibration, but I'm going to tend to start it with simple harmonic motion of some part of the medium. And then that simple harmonic motion transfers the energy to the rest of the medium, through the medium. So it travels, and when I say the wave travels, really what happens is that wave energy travels through the medium with some velocity. And the sorts of things we measure with waves, we're going to look at parts of waves, and we're going to look at timing, because there are things that have to do with the timing that are not so easy to measure without thinking it through carefully. So let's talk about the two different kinds of waves that we're going to look at. First one is called a transverse wave. And a transverse wave looks like a wave, looks like a water wave, looks like what we think of as a wave. In other words, it's curvy. Okay. A water wave is actually not quite a transverse wave. It's a little more complicated. So a transverse wave looks kind of like, if I asked you to draw a wave, you'd probably draw something like this. Okay. So that's what a transverse wave looks like. And it's all the particles are vibrating around, I hate that, are vibrating back and forth around an equilibrium line. So the equilibrium line is that horizontal line. And each particle, if this is a rope, it's going to be vibrating back and forth. Oh, sorry about that. My stylus isn't working perfectly. It's going to be vibrating back and forth this way. Trans means across. So the energy may be moving this way, but the particles are moving back and forth in place. And we're going to see some simulations that show that. So even though a transverse wave appears to be moving like that, it's really the energy that's moving down there. This hump is moving while the particles go back and forth. Very hard to visualize until I show you some simulations. The second kind is a longitudinal wave. And longitudinal, and I should point out for the transverse, particles vibrate or oscillate perpendicular to the wave velocity. Okay, so the wave velocity is going this way. The particles, though, move back and forth perpendicular, and that's, I think of with trans, across, transcontinental railway. A longitudinal, sometimes called a compression wave, the particles vibrate back and forth along the direction parallel to the wave motion or the wave velocity. And a longitudinal wave is kind of a funny thing, and it's kind of hard to draw. You can make it with a slinky, and I'm going to do my best to draw what it would look like. If you take a slinky and lay it down, and then you push in on it really hard, really fast and then pull back, you're going to get these little areas. If I do it rhythmically, if I move my hand in simple harmonic motion back and forth, you're going to get these what we call compressions that will move down in that direction. So there's the wave velocity. But each particle, if we just took a particle right there, I hate how it does that, we could show that it moves back and forth in place perpendicular, or excuse me, parallel to the wave motion. So if we just looked at that dot, it would be moving back and forth in place. Okay, along, perpendicular to, along the direction of the wave velocity. So those are the basic waves you're going to be talking about. What's really important for today is just being able to measure parts of, and we're going to concentrate today on transverse waves. In the next class, what we'll do is we'll look at longitudinal waves more carefully, and we're going to use those to talk more specifically about sound. Sound waves are longitudinal waves. Sound waves have these areas of compression and these areas that are spread out. And each of them are moving with that same velocity down there. Again, particles are moving back and forth, but the wave velocity moves down along the stream there. Transverse wave. A transverse wave, you can think of this as a rope or something where all these molecules are bound together. And if you lift one part of the rope, the next part comes, and then the next part, and the next part. But the particles all move back and forth transverse to the wave energy. So if you follow that top there, that high part there, it's moving across to the right. But the particles stay put. It's just energy that's transferred. So we call that the direction of the wave velocity. But the particles move back and forth perpendicular. Okay, and yes, on the screen they look to be up and down. But if you held the screen flat, they'd be going, I don't know, north, south, east, west. But perpendicular to the wave motion is the key thing. So if you follow any one of these particles, you can sort of see they're all going up and down the same amount. So it's almost like an optical illusion, but this rope looks like it's moving down that way. So energy is transferred down the line, but mass is not. Now, let's look at a longitudinal wave. And first, the longitudinal wave, it looks like these dense areas are moving down, okay? But if you follow any one particle, it's just bouncing back and forth in simple harmonic motion. Just like the transverse was moving this way with simple harmonic motion, perpendicular to the wave energy, this one's moving parallel, and we call it longitudinal. Longitudinal, along is a way to remember it. It's parallel to the wave energy. So if you think of this got pushed by something and then it pushes some other ones. It hits this, it hits those other ones, comes back, and so that energy that's being added at this end gets transmitted down there. Sound waves are an example of longitudinal waves. Sound waves they're sometimes called compression or pressure waves because you can see we've got areas that are very low pressure and areas that are very high pressure. The particles are all collected together. And so those high pressure areas, which are called condensations or compressions, move down here. In other words, the area that is compressed moves. The particles, again, just vibrate back and forth. Now, when we talk about longitudinal waves, I'm going to talk about amplitude for transverse wave. For longitudinal waves, it's a little more difficult to see the amplitude because you have to figure out how much these particles are moving back and forth from each of their equilibrium spots. Much harder to measure. Here, a string of beads, string of little green and red balls. And this is a piston that's going to move this green one up and down. Well, if the green one wasn't connected to anything, it would just move up and down in simple harmonic motion. You're going to see this go around because this, remember, simple harmonic motion is an analog to circular motion. This is going to make a sine wave, which is one dimension of circular motion. So this is going to go up and down. And as this green one goes up, this red bead is going to be pulled by it. They're connected. So it's going to get pulled by it. It will be just behind the green one. and this red one will be just behind that red one, and so forth. So in a way, this is transferring energy from the first bead all the way down to all the other beads. Now, what we're going to do is we're going to have that simple harmonic motion just continue, and this will be what's called a periodic wave. And more specifically, this is going to be a periodic transverse wave. Transverse because the motion up and down here, the motion of each particle is perpendicular or across or trans the motion of the energy transfer. So let's see what that looks like. Just give it a second. Okay. So you can see the green one's going up and down. This red one's following it. This red one's following that one. So they trail a little bit. It's almost like there's a lag going to the same place. But if you look at this green one, it traces the exact same path that the first one does, just at a different time. It appears that things, if you squint, it looks like everything's moving out the window. But if you look at each one of these particles, they're all just vibrating back and forth in place. So a wave transfers energy, and we call that the direction of the energy. We call that the wave velocity. It transfers energy in this direction, but the particles are moving perpendicular or transverse to it. So it's a transverse wave. Let me pause it for a second. There's some key things you need to understand about this. First of all, the parts. I'm going to talk a lot about these parts. That's called a crest, the ones with the highest point. The ones at the lowest point are called troughs, T-R-O-U-G-H-S. This is the equilibrium or rest line, that yellow line there. Okay, so we can see the vibration goes back and forth, symmetric around that equilibrium line. If we take this, there's something very specific that we like to measure. It's called the amplitude. The amplitude is the farthest point from the equilibrium position. When we did simple harmonic motion, right? We didn't do the amplitude from one end to another. We did it from the equilibrium position to the farthest point. Same kind of definition. So this amplitude would be almost 0.8 centimeters. And it doesn't matter whether you measure it above or below. This one is pretty close too. Okay, let me see. I get a little better. Center of mass. So it's very close to 0.8. 0.8 above and below. This says 0.75. I'm not completely seeing that. 0.75, maybe a little higher. Yeah, okay. So the amplitude is measured from equilibrium to the crest or from equilibrium to the trough. It's a measure of how much that transverse motion goes. Again, the energy moves in that direction. Another dimension we could talk about is this. How far apart are those crests from each other? And that's about 2.5 centimeters. Now, that dimension is called the wavelength. Lambda is the symbol. And that lambda is the same wherever you measure it. If I measured trough to trough, I'd have the same lambda. And if we measured from, for example, this green dot to the next green dot, that's only half of the wavelength. This is the full wavelength that they've put out there. Really what I want to say is, if I measure from one crossing, you don't go to the next crossing because that's not the same part of the wave. The wavelength is one entire cycle, one wave that has all the parts in it. This only has this part. So I have to go way out here to see one complete wavelength. So those are the things we'd measure with a ruler: wavelength and amplitude. Okay. Now let's talk about things that you can't really just measure from this. I mean, you could actually look down here and cheat, but let's watch. Okay. One thing we have an awful lot in physics is period and frequency. The period is the time for, in simple harmonic motion, one complete back and forth vibration. So if I said start, stop, that's one period. But there's another way to measure it with waves. I could say, next crest, I'm going to start, stop. So one complete wave passing a given point is also the period. So if you're standing on a dock, let's say you're over here and you're standing on a dock and you're looking down at the water going by, right? Coming out of the dock, coming out from under the dock. And you could watch it go up and down, and the time to go completely down and completely up is one period. Or you could say, hey, there's a crest, there's another crest. That time would be the period. Frequency is just the inverse of that, 1 over the period. Or we could set up a time and we could say, I'm going to start right here, and the next crest that comes along, I'm going to start counting. Start 1 full wave, 2 full waves, 3 full waves, 4 full waves. And if I stop the clock right then, I could say 4 waves divided by that time would be the frequency. Okay, waves per second, or hertz. So it's very useful to be able to measure multiple time-related things for a moving object. And I could make it a whole lot harder, because I could mess around with this and make the wave longer and faster and so forth. The last thing I want to talk about is velocity. And velocity is actually a function of the frequency and the wavelength. We'll talk about that next time. But you could measure the velocity by saying, okay, there's a crest there. Let me line up this with the crest. And I could see, watch this thing go down and time it. So if I say, let's start the clock and follow this, and let me stop the clock, it traveled about 5.1 centimeters in however much time that was. So I could take displacement over time, and I would have the average velocity. So those are ideas about the measurements. Okay, you've got easy measurements, amplitude and wavelength, that you measure in meters. And then you have the time measurements, which are a little trickier for a moving wave.